Hi friends, back with another video. In this video, we are going to learn about RBF-16 hydrology method. It is developed and recommended by the Ministry of Railways to determine the design discharge for the catchments having catchment having less than 25 square kilometers of the area. It is improvisation in the conventional rational method where where the limitations of the conventional rational method is up to 80 hectares, but with this improved RBF-16 hydrology method with consideration of the regional by consideration of the regional geography features which are incorporated in this improvised rational method. It can be used for the area more than 25 square kilometers. Okay, so let's just have some um, um, uh, let's understand more on the RBF-16 hydrology. So the RBF-16 hydrology is mostly used in the design of these railway bridges. So here, if you see, suppose I want to propose or analyze existing bridge or a proposed bridge at this location. So I need to delineate the catchments which is on the upstream of it. So all the catchment which is contributing flow to this near to this intersection point, I need to delineate it. Okay, so let's consider a example case of the uh, to design the to estimate the design discharge for the railway bridge. So we know the latitude of it. This latitude is 8 degree and 45 minutes, and longitude is 77 degree 45 minutes. We have the catchment area which is 2.95 square kilometers, which is less than 25, so which comes in the scope of this RBF-16 hydrology method. And the length of the longest stream course at this bridge site is 3.39 kilometer. So you can consider like this. So if you check this illustrative sketch, so here I have proposed the here this is the location of my railway bridge, and I have delineated the catchment. So this lang chosen this is the longest flow path. So this is the length of this longest flow path is 3.39 kilometers, and its catchment area is 2.95. Okay, and the height of the farthest point above the interest along the stream is 16.4 meters. So they are telling that difference between the longest flow point to this intersection bridge is around 16.4 meter down. So uh, that means the highest level of this catchment is 16.4 meter down at the level lower than this the intersection point of this catchment. This is the outlet point of the catchment. Okay, and the other data's input data they have given is the equivalent stream slope, that is 4 meter per square kilometer. Sorry, 4 kilometer per, sorry, 4 meter per kilometer. And this one, the height of the farthest point above the interest along the stream, 16.4 meter, which we have already discussed. And the catchment lies in the subzone 4C. So this is a uh, jo- the hydrology zonal classification for India. And the soil in this catchment is mostly plain dry cultivated. So they given the type of the soil in this catchment area. So this is the one of the major parameters they have included, because in this conventional rational method, so we will use the land use characters that for to determine the runoff coefficient. Okay, but here in this RBF-16 hydrology, we have this soil. We'll consider the soil characteristics and the catchment area characteristics, and the catchment area characteristics, that is the aerial reduction factor will be there. And we'll consider the soil, and So with these two parameters we are considered in majorly in this RBF-16 RBF-16 hydrology method. Um, so here we have this soil in the catchment. So it is mostly plain dry cultivated. So and we from this in from this information, so we will check the recommendation in the recommendation for the runoff coefficient in the RBF-16 hydrology. So if you check this here, this from this it is taken from the RBF-16 manual. So here if you see this runoff coefficient C for the different characteristics, here it is comes under dry cultivated soil, dry cultivated. So dry cultivated, we can use this number 3, red soil, clay, loam, and gray cultivated plains. So we can use this see a formula, that is 0.415 RF to the power zero point 0.2, where R is the 50-year rainfall depth, 50-year point rainfall depth in centimeters, and F is the aerial reduction factor, so which depends on this which depends on the catchment area and the duration of the rainfall. Okay, so first to calculate that, first we need to calculate these parameters. First we need to calculate the TC, that is time of concentration. So for time of concentration, so for the time of concentration, we have the Bhatnagar formula, so which is used to determine the time of concentration of the catchments in the Indian zone. Okay, so I have this formula. This is L cube to the power L cube by H to the power 0.345, where L is the length of the longest stream course at the bridge side, is 3.39. H is the height of the farthest point above the interest of the along the stream, that's 16.4 meter. So I'll apply this formula, and the TC comes in terms of hours. Okay, so L, we know it is 3.39 to the power 3 divided by H is 16.4, so to the power 345. Okay, so I got the value of the TC, that is 1.34 or 347. I can mention it as a 35 hours. So this is my TC value. TC. So TC value is 1.35. So this TC value I can use this TC value in the runoff coefficient to for this aerial reduction factor, to find the aerial reduction factor. Okay, and yeah, so in this runoff coefficient, C is equals to 415 RF to the power 0.2. So this is we determined, we have determined based on the soil soil in the catchment. So it is mostly plain dry, and we check this RBF-16 table, so which is mentioned in the RBF-16, that is the number 3, where they have mentioned the cultivated plain, and its formula 4.415 RF to the power 4. Okay, so we'll use that. Okay, yes, so we'll use that. There's this formula to so we know the to determine the R's, so we have to we have this I have this isopluvial data, so I'll have this isopluvial map, so I'll check this here. So this is for the subzone 4C. Okay, so I'll check this data here. So based on the latitude and the longitude, latitude I know it is 8 degree 45 minutes, and longitude is 77.45. So I'll locate this location in this map image, and I'll determine the rainfall depth. So I'll zoom this here. Okay, I'll zoom it further. Okay, so here This latitude is 8 degree 45 minutes. It comes somewhere here approximately locate, and longitude is 77 degree 45 minutes, so it's come somewhere here. So if you check this both value, it is coming around, it's beyond 220 limit, so it is around 220. Yeah, it coming around 220, so I will take this as 220, uh 220 mm. So this is 220 mm. This is r is equals to 220 mm. And in this formula, so in this runoff coefficient, we need to apply in terms of centimeters, so it will be 22 centimeters. And the f, that is the aerial reduction factor. So aerial reduction factor, to determine, so aerial reduction factor, we have this runoff, sorry, time of concentration 1.35, and the catchment area, which is 2.95. So we have this table. So we have this table. So we have the table. Yes. Okay. So we have this table. So what they have mentioned is the time of concentration is 1.35. So the time of concentration in the rational method is nothing but the duration of the rainfall. Okay. So it comes. It is 1.35 hours. It's more than 60 hours. Sorry, 60 minutes, and it is less than 100. Okay. So now we will find in the next parameter, that is R50 TC, which is equals to K into R50I. The R50I is nothing but the 50 rainfall depth of at a 50-year return period. So which is we already found, it is 220 mm. And the K factor, so K factor, that is based on the time of concentration value, ratio value based on the graph. So I have the I know the catchment subzone, that is zone 4, and I know the value of the TC, this is 1.35. And so I will mark that in the graph I have, and to find this uh, TC ratios. Okay. So I'll have this graph here. Okay, I'll zoom that. So TC is 1.35 for the zone 4. Okay, approximately I'll mark, because it's very this page is slightly distorted due to this old print. So I'll mark the approximate value of the TC ratio. Okay, for TC ratio for the 1.35. So 1.35. So I'll mark this 1.3. Each unit is point zero 0.05 hours here. So 1.25, 1.35, sorry, 1.3 and 1.35. Okay. Okay, 1.35 for the zone 4. Okay, zone 4, it is coming around here. Okay, so in the, so it is coming around point 46, I can say 47, 465 approximately. I'll consider it as a point 465. Okay, 465 will be my TC hour for the 1.35 TC hour. So TC hours for the 1.35. So TC hours. So TC hour is I'll just type it here separately. Okay, TC hour ratio. Okay, that is for the 1.35. That is 1.535 TC. That is mm, that is 0.465. That just we have marked in the graph. And the second one for the 1 hour TC hour ratio. Okay, so 1 hour TC hour, 1 hour, sorry, just miss TC hour ratio, TC 1 hour ratio. So 1 hour TC 1 hour ratio. So TC hour ratio we found is for 0.465, for the time of concentration 1.35. So TC 1 hour we need to check for the 1 hour duration of the TC in 1 hour. So TC in 1 hour is here. Same it's for the zone 4. I'll zoom it here. Okay, it's 1 hour. Okay, okay, 1 hour. I locate it. Mm, so here this is the subzone of subzone 4, sorry, zone 4, and locate it's around 4 2, I can say around 4 2 it's coming. Okay, so this is the location. It's around 415, 41, I can say. The zone 4 is 41. Okay, so this TC our one TC 1 hour ratio is 0.41. Okay, so I'll calculate this K factor. This K factor is ratio of TC hour ratio to the TC 1 hour ratio. Okay, TC hour ratio is 0.465 to the power sorry, divided by 0.41, so it is 1.13. Okay, 1.13, 1.13. We have found the values of the this K factor. So K factor, that is the ratio of TC hour ratio to the TC 1 hour ratio. So it is coming to be 1.13. Okay, so now find the next parameter. This is RTC is equals to R50 corresponding to TC. So that is equals to K into R50I. So we know the for to find the R50I. So we know the 50 rainfall depth for the 24-hour storm, that is 220 mm, or you can say 22 centimeter. So this value we will multiply with the time of concentration of the 1 hour. That's TC hour 1 hour ratio. So TC 1 hour ratio is 0.41. Okay, so I will calculate this R50I. So R50I is equals to the 24 hours 50 or 24 hour storm is 220 into this TC 1 hour is 0.41. Okay, so we found the uh, this R50I, which is coming to be 90.2 mm. So we'll put that 90.2 mm here in this R50TC. So R50TC, we'll calculate the R50TC with this R50I. Okay, K factor we know it is 1.134 into this R50I is equals to 102 mm. Okay, this R50TC, with this R50TC we will use it in this rainfall intensity formula. This is R50TC by TC. TC we know, which is already found, it is 1.35, and this R50TC we need to apply this in this equation. This R50TC divided by this TC is 1.35 hours. So 1.35 hours. So the rainfall intensity we found is 75.88. Okay, so we will use the RBF-16 formula. So that is the improvised rational method. Okay, so we will use this formula. It's Q50 is because it's taken from the it's taken for the considered for the 50-year design storm. So that's why I mentioned Q50. That's why it is mentioned Q50. Okay, 0.278 is the conversion factor, and C is the runoff coefficient is 0.75 into I is the rainfall intensity which we calculated. It's 75.88 into the area. So area of the catchment is 2.95. Okay, so the discharge for this design discharge for this bridge is coming, for this proposed bridge is coming around 46.767, or I can say it is around 47 meter cube per second. Okay, will be the design discharge. Okay, so this is the final design discharge. It is 46.67, I can say 47 meter cube per second. Okay, thank you for watching.